In the previous lecture, we introduced the notion of four vectors. This is a set of four quantities which we place in the form of a four vector because we know the transform from one reference frame S to the other reference frame S prime using the same Laurent transformation. We have learned one important four vector already, and that is the space-time four vector. Now we have another one, the so-called energy momentum four vector. This is the way to write it. E as the first component, and then the next three components are pxc, pyc, and pzc. Px is the x component of the momentum, and so on. Of course, we already know that energy E can also be written as gamma mc squared. Px is gamma mux, and so on. This gamma, in fact, is gamma u, not gamma v. I want to make a distinction. Gamma u. Because when you calculate this gamma, it's based on the speed of the particle u, not based on the speed of reference frame v. So we can plug these expressions in and we get these four components of the energy momentum four vector. Here is the energy component, here is px, py, and pz. We did not show that this, in fact, is a legitimate four vector. The way you show it is to show that indeed the first, second, third, and fourth component of this energy momentum four vector transform like that. For example, you need to show that the first component, which is x naught prime, or since x naught equals this, gamma u prime m c squared, must equal to this. This gamma is for v, for the between the two reference frames, v. And then x naught, which is gamma u mc squared, minus beta. Beta is v over c. And then x1, this is x1 right here, gamma u mux c. Okay, you can cross out those mc squared terms, and you can come up with something a little bit simpler. Gamma u prime equals gamma v, and there's a gamma u in both terms. You take that gamma u out. Mc squared, you just cancel from here. 1 minus uxv over c squared. If you can show that, then indeed the first of these transformation formulas for the four vector holds true for this particular four vector. This is a little tedious to do, but it can be done. You notice that u prime is the speed of the particle in the s prime frame. We have its three components, ux prime, uy prime, uz prime, as a function of ux, uy, uz. This is from relativistic velocity transformation that we learned in the previous lecture. So if you plug that in after some tedious algebra, you are going to get this. You can see it for yourself. You can also show similarly how the other three can be verified. And so indeed, without going into further algebra, I want to tell you that this indeed is true. You don't have to take my word for it. You can show that for yourself after some tedious work. We are going to be using the energy momentum four vector in a special case later in this lecture. Now that we looked at both the energy and momentum in a relativistic particle, let us look at how we can connect energy and momentum together. You know, classically, the energy or the kinetic energy of a particle is related to its momentum like this. 1/2 mu squared, but mu is p, so I can write this as p squared over 2m. That is the classical case. For the kinetic energy, of course, don't forget you have to also add the rest energy, not just the kinetic energy. This is the total energy. The rest energy is mc squared. This is when u over c is far less than 1, classical case. Now, in the relativistic case, this has to be rewritten. So what is the new formula we can come up with that relates energy and momentum in relativity? The general relationship between energy and momentum of a particle is called the dispersion relation. And this is the low speed limit for the high speed case, the new formula is this. E squared equals to m squared, mc squared, the whole thing squared, plus p squared, c squared. So you take the square root, you will get this new relationship. Okay, how do we show this? That's quite simple to show. All you have to do is plug in the expression for E and P. For E, I have E equals gamma U mc squared. You take this thing squared, is it really equal to this plus that, which is mc squared, the whole thing squared, plus p squared c squared. P is gamma U m u, and then times c squared. Can we see that? Well, this in fact not that difficult to show. It is not all that tedious at all. All you have to do is write down the expression for gamma u. In fact, all you need to do is gamma u squared, and then have another gamma u squared, and you can easily match the two sides to see that they are equal to each other. So therefore, if you take the square root, you find E to be equal to the square root of mc squared, the whole thing squared, plus p squared c squared. Okay. Again, this looks very different from the classical case, but if we're looking at low speed motion, in other words, the momentum is not very large, or we say the kinetic energy is far less than the rest energy, then the second term is a lot less than the first term, and we can make the same approximation as we did before. Before we do that, let's first box this, because this is the most general expression. Okay, so as PC is far less than mc squared, then what is E equal to? Well, I can take that mc squared out of the square root. So this is mc squared. What's left is 1 plus PC over mc squared, or P over mc squared to the power 1/2. Right? There's no approximation, but next thing I'm going to do is I'm going to approximate, because I know that this 1 plus nx, n being 1/2, x being p over mc, which is very less, much less than 1. So this is approximately 1 plus nx, so it's 1 plus 1/2 p squared m squared c squared. Okay, work this out. The first term is mc squared, which of course is rest energy. The next term is p squared over 2m. That's exactly the same as we expected. So this expression reduces to the classical case at low speeds, as we should expect. If we plot E as a function of PC, or as a function of P, what do we get? Well, when P equals 0, I get E naught, which is mc squared. And the curve looks like this. Classically, this is a quadratic term, okay? It's a parabola, and it will look like this classically. But in relativistic case, at low speeds, it's a parabola. At high speeds, when the next term, the kinetic energy is far greater than the rest energy, you can ignore the rest energy term, and E equals the square root of p squared c squared, just pc, which means this is linear. Linear. This is quadratic. Okay, so when E is approximately equal to PC, we're looking at a very high speed particle. This is called ultra relativistic case. Now, what if m equals 0? What do we get there? Well, classically, if the mass is equal to 0, you find this particle doesn't even exist, right? But we're talking about the rest mass. Okay, we're talking about a rest mass. When the rest mass is equal to 0, is it true the particle necessarily does not exist? Well, I can write E as m gamma u times c squared. That's the total energy. Right? That's the total energy. Now, the rest energy is zero because there is no rest mass. But is it true that the total energy is always necessarily zero? If you look at it in mathematics, what do you see? You get m times gamma u. Now m is zero. So normally E would be zero, but what if gamma u approaches infinity? Or if it's exactly infinity? Then you have 0 times infinity. Is 0 times infinity necessarily zero? Of course not. So you see, mathematically we find that even a massless particle, which means it's got no rest mass, may still have energy, which means it may still exist, but there is a requirement, and that is it must travel at the speed of light, because that is the only time when gamma u can be equal to infinity. Okay, so that means u is equal to c for this particle to exist at all. So can we think of a particle whose rest mass is zero and it travels at the speed of light? Yes, the particles of light themselves are just like that. Particles of light, of course, they travel at the speed of light. These are called photons. Another example, at least we believe, neutrinos. That's another type of elementary particle. They have no rest mass, and therefore they have to travel at the speed of light. Any massless particle must travel at the same speed, which is the speed of light. Otherwise, they will have no energy, which means they do not exist. As I make this recording, there has been a recent finding, supposedly by a group of Italian physicists working on the so-called opera apparatus. What they did was they measured how fast a beam of neutrinos would propagate from one facility to another, and they found, according to their data analysis, that the neutrinos traveled faster than the speed of light. It arrived sooner than light by a matter of some nanoseconds, about 60 nanoseconds. They claimed that their experiment was accurate, but most physicists reacted to this with a lot of skepticism. In fact, if you ask me, like most physicists, my reaction to that is the experiment is probably wrong, because neutrinos, as we know, have no rest mass. They do travel the speed of light, but they cannot go faster than the speed of light. Anything that travels faster than the speed of light would have a gamma factor that is imaginary, and that's not correct physics. But what if their experiment turned out to be true? God forbid. If their experiment turned out to be true, then the theory of special relativity as we know it will have to be rewritten, and our notion of space and time will once again be undergoing a revolution, just like what Einstein did. I'm highly dubious this is going to happen. My bet is that the experiment is wrong, but this is still an ongoing event. We'll see what happens. As an example of the energy momentum 4 vector at work, let's consider the energy momentum 4 vector of a photon. As we learned, photons are massless particles, so they have to travel at the speed of light. And their momentum is related to their energy with E equal to pc, because in that energy momentum expression, if you cross out m, the rest mass, you're going to get E equals pc, or P equals E over c. But what about the energy itself? It turns out, as we'll learn in a later chapter, that the energy of the photon is proportional to its frequency. And there is a constant of proportionality h, which is known as the Planck's constant, but right now we just call it a constant h. So E equals hf, but P must equal to E over c according to Einstein's relation between energy and momentum, so that is hf over c. So let's consider a photon, a beam of light, which is made of many, many photons. One of these photons move with a speed c in a direction which makes an angle theta with the x-axis. Okay, with the x-axis. And then let's write down the energy momentum vector, 4 vector of this particular photon. We have E equals hf, and the linear momentum px, py, pz, which is hf times c. Now multiply by c again, you just get hf. So the magnitude of the momentum times c is just hf, just like the energy. But here is the s component, so you have the magnitude, which is hf, times cosine theta to get the x component, and then the sine theta represents the y component, and it doesn't travel along the z direction, so it's 0. for the last component. So this is the energy momentum forward vector for this photon in the S frame. Now suppose I watch this photon from the S prime frame. Okay, from the S prime frame, and S prime moves this way along the S direction with a speed v. So in S prime frame, look at the same photon. What is the energy momentum forward vector? Then I will be getting E prime P prime C, right? And this is equal to HF prime cosine theta prime, HF prime sine theta prime, and 0. That tells me that in this new reference frame, if I watch the same photon, it is not going to have the same frequency. F becomes F prime, and moreover, the direction of propagation of that photon is no longer an angle theta from the x-axis, rather is an angle theta prime from the x-axis. So this photon will have different frequency or different color and will appear to move in a different direction. Let us find F prime in terms of F and theta prime in terms of theta and so on. How do we do that? Well, we know how to go from here to there because all four vectors go through the same exact transformation. So let's do that. As a reminder, this is the energy momentum this is how any four vector transform. We have seen this a number of times before. X naught is equal to HF, so that's HF prime in S prime frame equal to gamma times X naught, which is HF, beta x1, x1 is HF cosine theta, as you see here. And here's x1 prime. X1 is HF cosine theta, so HF prime cosine theta prime equals gamma times x1, which is HF cosine theta right here, minus beta times x0. x0 is just HF. This pair of identities tell us how to find F prime and how to find theta prime. So let's solve for F prime and let's solve for theta prime. In fact, all we have to do is cancel out the power, the quantity h, and you have for yourself F prime equals gamma times F, and then 1 minus beta cosine theta. And then you can also find theta prime in terms of theta now that you already know how F prime is related to F. So if you solve for cosine theta prime, also using the ratio of F over F prime from what we get here, this is how the angle changes. So that's cosine theta prime. We have now found what the frequency will look like in a new reference frame and what the angle of propagation will look in a new reference frame. You can cross out this gamma factor here. F prime, once again, equals F times 1 minus beta cosine theta times gamma. Gamma itself is 1 minus beta squared. And this cosine theta prime, copy this, is cosine theta minus beta divided by 1 minus beta cosine theta. This is the pair of equations we're looking at. And this is the formulas for relativistic Doppler effect. Okay, you remember Doppler effect? Doppler effect says that for a beam of light, well, in any wave, it could be light, it could be sound, if the observer is moving or if the source is moving, the frequency registered by the observer will be different from the frequency emitted by the source due to the motion of the source and or the observer, right? We had a derivation of the so-called classical Doppler effect using the motion of the source and the observer. We cannot do the same type of measurement here because the motion of the source and the motion of the observer in classical case were both measured with respect to the stationary frame of the medium, right? But there is no such thing as the stationary frame of medium for light. Light does not have a specific medium in vacuum, remember that? So the only thing that actually still makes sense is the relative velocity between the two observers, S and S prime. There is no such thing as absolute speed of the observer and absolute speed of the source relative to the stationary medium, because the stationary medium does not exist. So as a result, the formulas are also very different. If we take a look at a special case where theta equals 0, okay, so if photon shoots this way, and I watch it while I'm moving towards it. If I watch while I'm moving towards it, this v in fact is reversed, right? So I can take that formula, I have to reverse that v, and don't forget I also have to take theta equal to 0, so cosine theta equals 1. So this is what we have. We have a photon moving towards the positive x direction, and an observer moving with a speed v from the in the s prime frame towards the source s. What does he see? Well, f prime equals the formula we used before here. Beta becomes negative beta because we're going backwards. Cosine theta becomes 1, so you have this, right? And you do that algebra, you find there is a square root here. Now, classically, a beam of whatever wave comes this way, and the observer moves towards it, you're supposed to getting 1 plus beta. Beta is the speed of the observer divided by the speed of the source. But here I have this very different formula. There's square root, and there's 1 plus beta of 1 minus beta. So you see, we're looking at a different formula, relativistically versus classically. And the radar gun used by the police actually uses the beam of electromagnetic wave. In particular, they use microwave. Okay, radar is operates in the microwave range, and the police shoots a beam of radar beam at you. It bounces off your moving vehicle and comes back. The frequency is shifted due to the relativistic Doppler shift formula, and the radar gun used that frequency difference using this formula to calculate to find beta based on f prime and f, and from that it can deduce your speed. So, if you got a speeding ticket from the police's radar gun, you can thank Albert Einstein for his great discovery. The last thing I want to talk about in the relativistic Doppler effect is what happens when you move at very high speed towards a source of light. So v is very large. Okay, v is so large, v is almost equal to c, therefore beta is almost equal to 1. Look at the formula for angles. So I have now cosine theta prime is roughly equal to cosine theta minus 1 and divided by 1 minus cosine theta, right? Look at this, because beta is almost equal to 1. And this is about negative 1. You know what that means? That means this beam in the s prime frame, this beam, regardless of the incoming direction could be like this, you know, hf, the original direction in the s frame. Cosine theta prime is almost equal to negative 1, which means theta prime is roughly equal to pi. Pi means it's going towards you instead of leaving you, moving towards you. So basically this beam becomes highly concentrated, okay? If the original beam is in a variety of directions, this beam becomes highly concentrated if you move at high speeds towards the source. So the beam becomes very narrow, collimated. This is called headlight effect. This is something unique for high-speed propagation. Before we end our discussion about relativistic Doppler effect, let's take a look at one last special case, and that is when theta equals 90 degrees. Well, classically, if a beam of whatever wave, such as sound wave, propagates in a direction that is perpendicular to the line connecting the source and the observer, here's the observer, here's the source, then there is no Doppler effect. There is no change in frequency. And that is because as the wave propagates this way, the motion of the observer is not really cutting into the wavefront, and as a result, the Doppler effect does not exist. Now, what happens in the relativistic case? Well, all we have to do is plug in theta equals 90 degrees into the formula. This is the formula we learned a minute ago. And when theta equals 90 degrees, cosine theta is equal to 1, so that's gone. But there is still a square root of 1 minus beta squared in the denominator, and that is in fact the gamma factor. So you see here, even when a photon propagates perpendicularly to the direction of motion of the observer still observes a frequency shift because of this gamma factor. And the reason why that happened here is because even though there is no cutting into the wavefront, as in classical case, there is something still different between the source and the observer, and that is the observer is moving towards the source. He is in a different reference frame S prime, and that different reference frame has a different clock compared with the S frame, and that is what's causing this gamma factor here. So that is the so-called transverse Doppler effect, which did not exist in classical physics, but it does exist here because of the time difference between these two reference frames.